Okay, good morning, everyone. Welcome to this event, which is associated with the closure of the project design of cooperative energy-aware aerial platforms for remote and contact-aware operations. The acronym is DOCEAT. The event is part of the Road to CDC 24 series of events, which has been organized by the Italian chapter of the IEEE CSS. It's a pleasure to host the event in person at Politecnico di Milano at the Department of Aerospace Science and Technology. And I will immediately pass the mic to Professor Alessandro Astolfi, who has been the coordinator of the project throughout the activities. Alessandro, please.
Thank you, Marco, for hosting this event. So my name is Alessandro Astolfi, and I'm the coordinator of this project, which involves, the University of Rome, Tor Vergata as coordinator, and then the University of Trento, Padova, Politecnico of Milan, and Bologna. So the role of the project is to design new drone platforms with the idea that these platforms should interact with the environment. So we don't only have drones that are sort of flying for surveillance, for example, but we would like to get drone to inspect critical infrastructure or for disaster recovery. And so we put together the expertise of 5 groups that have been working on autonomous system and drones over several years. And today we are going to present some of the scientific results that have been developed throughout this project. So the presentation will be in order given by Sergio Galeani from the University of Rome on controlling the observer design tool for a fleet of UAV. Then Luca Zaccarian from University of Trento and CNRS France, where he will be discussing a problem associated with controlling a unicycle using a hybrid strategy that uses cameras for navigation. This is followed by a presentation by Nicola Mimmo from the University of Bologna on bearing-based target localization in search and rescue scenarios. And then Giulia Micheletto from the University of Padova. She will she will discuss and present results on star-shaped tilted Hexarotor maneuverability. And in particular, she will highlight the role of the tilt angles in this task. And last but not least, as they usually say, David Invernizzi, that we also have to thank for doing quite a lot of the logistic and and Julia, sorry, I apologize. And Julia also we have to thank for doing quite a lot of the logistic and organization problem and sort of to keep us to schedule, so to speak. Is going to present work on adaptive plant augmentation design with application to multirotor UAVs with tiltable propellers. So thank you very much for attending in person and for attending online. And we'll now, I think we can now move to the first presentation. Yeah, thank you.
Si sente così? Perfetto, ok.
Qua? No? Bisogna di là che è più ampio.
Ok. Okay, so welcome you everybody. I am actually going to be the presenter, but the actual work of that you will see in the slides, well, it's always complicated because you have a long project and there are several things going on, several branches being studied. So it's always kind of complicated to select one topic or select a certain number of topics and try to give the idea of what has been done during the project. So what I will try to do is, in the slides, what you will see, the slides were assembled by different people working in our unit in Rome Tor Vergata, and so you will see also different ways of presenting things. Okay, so this is well, the list of possible topics. I don't know if I will be able to cover everything in this talk, but mainly the idea is to start with describing some of the work that has been done with autonomous agents. Most of these has been work done in the context of a Leonardo drone contest, which has been running through several years. So it was, let's say, ground tested also in this competition. The second point will be something much more specific, trying to focus on a specific algorithm for observer designs, trying to combine ideas from high-gain observers for uncertain systems and the use of interval mathematics to deal with strictly bounding the uncertainty going on our system during the observation. The third part, which is possibly something that I've been in several fashions more involved into, is about dynamic input allocation. And it has a direct bearing on drones, especially over-actuated drones. But most of what I will talk about, if I manage to arrive there, will be also on a different application. So we have been trying also to do some kind of cross-coupling between domains. And there is some final slide of some other work in progress, which I also think is important, meaning that what can one opt for better than to say, okay, we have done some project, but what we have been studying is not done. Actually, we are seeing that we are new ideas, we have new developments and things that we want to investigate on the basis of what we have already done. So let's start with the first topic. So part of the work that has been done has been also starting really from ground zero, so to say. So this thing that you see in the subtitle is related to this Leonardo drone contest I was talking about before. So there has been a group, especially of our PhD students. Professor Carnevale had a strong role in there as well, that have been developing drones. Some of them were just off-the-shelf objects. Some of them were built, let's say, in-house. So they have designed, they have done their own tries, which maybe here might be something more familiar to all of you. But for our group, we are essentially a control group, and there is no specific aeronautical base. So it's quite a challenge. So they have been developing this. They have been developing or assembling, coordinating the whole stack of the software required. And this is one of the drones that I built. This is one of the drones that I built. They also built a bigger drone for a higher payload and for more, let's say, challenging tasks. The second kind of object, this was recently, well, let's say, recently got in the team of the group of drones they were dealing with, is a quadruped, so essentially a sort of dog, here in the picture, a sort of robotic dog. And again, some of the equipment on board is similar, and this is also part of some that they factor on in their work. Why? Because one of the big works that they have been doing has been in constructing a distributed architecture, distributed from the point of view of, let's say, software engineering, so having several different software agents dealing with stuff, communicating in an asynchronous way with heterogeneous hardware platforms. And the part of it was, I mean, part of the whole work was not just to have this thing work on a specific set of platforms, but making it as replicable as possible, as modifiable as possible according to your need. So it is really the idea of having, for example, Docker containers in such a way that things were pluggable and unpluggable in a very easy fashion and replicable from machine to machine. Integrating different other software tools or middleware tools that were partly available, partly not. So, for example, there has been a lot of work on translation and developing software layers to have ROS2 to chat with all the other pieces that weren't really available before. And for example, one of the good things that came out of confronting or participating in the drone competition, for example, was that they were relying a lot on transmission over Wi-Fi, and it turned out that when they went on the actual competition ground, nothing worked. I mean, the communications were just going terribly down. Maybe some of you was there and saw it, experienced it. So part of the work, again, was to go back and see, okay, how much do we need to communicate? How can we counteract these possible problems of communication that we have been experiencing? And so they did a pretty good job at that, and actually in subsequent trials, things were a lot much better. Okay. So again, in this whole thing, actually there are a lot of topics related to this part of the work. So one of the problems that they have been facing and that have been the subject of research during this time has been on algorithms for sensor fusions. Now this is pretty at a high level, but the basic idea is that we have different sensors based on different platforms, and they all see the world in a different way, if not for any other reason, just because they are located in different places, they see different scenes, and we need to combine all this information. So it is a well-studied problem how to combine different readings into a coherent image or a coherent story about, for example, the place we are visiting or where we are in the place we are visiting. This is the usual SLAM problem of understanding how the place I'm living in is done, so to formulate a mapping, and a map of the place and localizing myself inside the map. So the algorithms that they started from were the usual Kalman filtering ones, the methods based on probabilistic methods, let's say, and approaches trying to combine deep learning into this problem as well. The idea was to try to go past the need that some of these methods have in different degrees. The need to have accurate models of the sensor or the dynamics of the agent that is carrying that sensor, as well as the need of have high computational power to combine all the information. And this is especially true in the case of visual sensors, where we have to look for features in the environment, try to combine them, try to contact other agents and see if they have, if they see the same features, how to combine the two scenes. So the idea was to work on this on this hypothesis and try to say what can we do if we don't have this information or we don't have a reliable version of that information. So this is one of the algorithms that, well, the assumptions, and I will try to get into the algorithm that they have been using to combine these things. And so they are assuming essentially that, okay, we have discrete time measures, of course, because we are, if not for another reason, we have limited communication, we have visual sensor, for example, that go on a low sampling rate because we have to take this image, elaborate the image, and so on. They are assuming to have a certain number of different sensors that we will call SI. There is a coordination assumption about the sampling periods, so they are assuming that there is a common sampling period for all sensors, and they are essentially coordinated. So this is one of the versions of the algorithm. And so for each one of the sensors, they essentially they are assuming that there is some measurement done of position, essentially. So at time k, at discrete time k, we have a position for sensor I characterized by its position in the x and y coordinates. And we have another information which is an on-off value that essentially is a small s I subscript ik. Essentially, this is telling us if this specific height sensor is working on or not at time k. And so the goal is to design a structure, actually a blending map, it is called here, a blending map which, using this information, so the first n arguments in the blending map are essentially the position measurements from the sensors. The subsequent n values are telling us which sensor is on and which sensor is off. So we could have one of these measurements which is actually corresponding to an off sensor, which means we shouldn't rely on that. And so the output of this map is a blended position estimate at time k derived through this map, capital B. And the goal here is to design this sensor fusion algorithm implementing the mathematical map B such that we are not using any more information from the agents than this information here. So we are just using position, sample, and functioning states. So this is just making more explicit what is already written in the formula. And the second part is to say that we want this map to be efficient from a computational point of view and possible to require as little hardware resources as possible, in addition to what is used to make the sensors work. And so the final algorithm is essentially some sort of weighted combination of the measurements that we have. So there is a different notation here associated to the whole information that we saw before. So the delta bar contains all the position measurements from the different sensors, and this S bar k collects the functioning states of the different sensors at time k. So we are essentially making a weighted combination of the elements of the position readings from the sensors, and the weights in this linear combination actually are computed just using the let's say the functioning states of the single sensors. So here it's the functioning state of the height sensor, and we have this thing here that essentially is considering the state of this sensor, the height sensor, with respect to the overall state of the whole set of sensors. Okay, so actually in here we have these weights alpha I, which are parameters that are that can be tuned to account for different things happening. So they have an effect on accuracy, on let's say we can change those alpha I to replace one sensor that is failed to give more importance to the functioning ones, and the operations that are required to compute this thing are essentially quite basic, so they can be done efficiently on the available hardware. Okay, so I will not go much into details, but here there is some sort of experiment that was done. So there are waypoints along this white region, and there are obstacles, so we don't want to run into them. We want to go from waypoint to waypoint. The point is that while we are going through the path, we have different sensors. So the red one is essentially using the ORB-SLAM2 algorithm. The second one is the position estimates from the Z-Mini camera. The blue one is the fusion of the two readings. Now, what is interesting here is the red dot and crosses that you see along the path. Actually, the red dots tell you when the ORB2 sensor is lost, meaning that we are simulating a failure just putting something in front of it or disconnecting the cable on the robot. That is alimenting the ORB-SLAM algorithm. And then when we are in the red dot, we are okay. So sorry, we lost the ORB2 sensor when we are on the red dot, and we are getting back the sensor when we are on the cross. Okay, so we reset it, and it will start giving us some measurements again. And so, I mean, the take-home message is that using the simple algorithm that I just showed you is able to recover quite some robustness from these two sensors, despite the failure. You see that the blue track is following quite closely the dashed line, which is supposedly the true reading that we want to have. So this was some paper telling about this, published in a conference we had last year in Rome. Okay, so this was part of the whole general thing. So sorry, let me also check on time, that I don't want to. I know that there are angels watching on that, right? But okay. Okay, so there is the whole stack that have been developed for allowing the navigation. So what I've been telling you before is just a little part, and then it is inserted in a bigger picture, of course. So the whole navigation stack includes some reconstruction of the environment based on detecting voxels in 3D. And then there is a tessellation of the space, so that using this Voronoi, we can this Voronoi tessellation, we can give a structure to the free space, and we use this structure for running a classical A-star algorithm for finding a path on the graph obtained by the Voronoi tessellation, and so the trajectory is generated and followed by the rest of the stack. Okay, so I'm not going into details, but again, this is a quite suggesting image, where it is pretty easy to see the voxels that have been captured in red, the Voronoi tessellation. So it's something described by these big void volumes here, and the path that has been found using all this information. Okay, so the second topic that I will talk about, as I was telling you, is essentially a kind of a very punctual thing, just an example of things that have been done. considering that drones are typically affected by several nonlinearities and uncertainty, and we are only able to measure some quantities, not everything described in the drone. Maybe we have a wonderful control law, but we don't have available measurements of all the state variables, for example, that we need to implement it. So the idea is let's try to build some easy estimate of the uncertainty and of the variables of interest. So this is also some work that has been published, where the idea is to try to combine high-gain observers using sample measurements, because it's what we have in a similar scenario, and using interval arithmetic as an additional tool to have a simplified design and to try to capture, as I was saying, the uncertainties on the system. Okay, so the basic setting is quite classic. Essentially, it's a nonlinear system in observability canonical form, which we are assuming holds globally. We will see on an example that you can run this algorithm on something that doesn't respect this hypothesis and still get useful information, okay? Okay, so we have the state xi. This is our system. Phi is essentially subsuming all the nonlinearities, which depends both on state and input. And we have, in this case, a scalar input and a scalar output, okay, which is the first, let's say, the first output in this chain of integrator. That is the linear part, and then you will have the nonlinear part, let's say, acting on the last state. Okay. So the idea is that we only have access to measurement, well, corrupted measurements of u and corrupted measurements of y, possibly. And we have an interval estimate of the initial condition. So this vector xi0, the initial state of the system, is inside this object, which also in its form resembles a box. So you have to imagine that interval estimates means that for each component of this vector, we have a lower and upper bound at time 0. And these lower and upper bounds will move in time as well as each component of the vector. Okay? So what we want to find actually is not just to find an estimate of the state, which will be in some box, but we also want to determine this box. Okay? So we want to determine how this box evolves, knowing the initial uncertainty that we have on this state. Okay, if you look at the scalar case, which might give us some intuition, in the scalar case, so you have not only a scalar u, but also a scalar state. What we are saying is that our measurement of the input is some nominal value plus a box. So in this case, it's just an interval, a symmetric interval, let's say -1 meter plus 1 meter, or I don't know, -1 Newton plus 1 Newton. And then for the state, which is also a scalar, again, we have a symmetric interval for this state. So if you just try to propagate these, it's pretty simple to write down what happens. Essentially, you have a direct, you can say that at time t, your state will be in the direct propagation of the original interval in your initial condition. And this is propagated by whatever dynamics you have. If A is positive, this term here will be increasing in time. If A is negative, it will be shrinking, and we are fine with that. Then you have the effect of the forced response on the system given by the nominal value of the input, and then you have the propagation of the interval. So essentially you are assuming that the bounds on this thing are constant, and you are just putting together the response of the system to this constant input. Now, if your system is stable, as I was saying, this thing tends to die out, and you can see that as time goes by, essentially here, if T1 was 0, this would actually be 0. Okay, so it's just a point. And when we go on, you see that as time goes on, this thing becomes smaller, so this whole interval increases, and it's always bounded by this quantity. So what we are hoping for is that if we can make the error system stable, we actually have some finite bound on this. Okay, if we move to the vector case, so the scalar case is somewhat easy and no surprise. Now, without going into details, but essentially when the thing becomes a system with n-dimensional state and possibly m-dimensional input, you can find that there are pairs of matrices A and B. All the eigenvalues of A are distinct, so you don't have strange things like Jordan blocks or so, or similar things. They are real and they are negative, so distinct, you have no oscillations, they are real and they are negative, so everything is shrinking. And yet, you look at this term, which is essentially this is essentially the error that was in this capital U here. You look at this thing and find out that this thing does not remain in the analogous term, the one that we had here, okay, and that we could bound like this in the stable case. Essentially, you have that your box doesn't behave nicely. I mean, you cannot just propagate the box in this way. So we have to come out with some different thing. Some smarter thing that than the one that you can use in the scalar case. Note that all the computation that you see here are intended to be interval computation. What does it mean? It means that when we do these products, okay, so U is a box in an m-dimensional space in this slide, okay? So let's say in 2 dimensions you have a square, for example. When you multiply by this thing, your square becomes slanted, okay? So you don't have just 2 intervals, but you have something that is different. So saying that we are doing interval computation, even though the notation doesn't tell, means that when we have this slanted parallelogram, we are putting a box around it, the smallest possible box, okay? And the result of this product is assumed to be the resulting box, okay? So it's kind of tricky, and I'm at least I should be able to finish this point. So there are 2 integration mechanisms essentially trying to recover what we could do in the scalar case. One of them is to try to do a change of coordinates to make the dynamics diagonal, and since all eigenvalues are distinct and negative, it means that we have just a bunch of scalar systems, okay? On scalar systems, we know how to propagate things, and so the only thing is that you have to bring the box here to the new coordinates, and after you do all the propagation, and in the scalar case this thing works to give a bounding box, then you have to go back in the original coordinates. So the trick here is that when you do this thing and when you do this thing, essentially you are slanting your boxes, and so the interval computation will require you to put another box around it, so you introduce conservativeness. So okay, so this is the first approach. The other approach that you can use is to use some slightly smarter thing, saying that you can always, let's say you have this Q, which might be, for example, this matrix here, okay? You have this Q that is a function of t minus tau, so there will be essentially inside here, let's say, the natural modes of this dynamics multiplied by some coefficients, okay? So what you do is you separate the positive and the negative coefficients, okay, with sign. So you always can do this decomposition in an analytical way to separate the positive and negative ones. And when you do these, essentially, without going into many details, but the idea here is that you are separating the positive and negative part, and you are propagating your box using always a plus sign for the positive ones, as was it in the original case, and the plus sign for the negative one, whereas in the original matrix you have a negative sign in front of this. And you do this, you don't have the problem related to the slanting due to the change of variables. And this thing actually gives you an estimate which is called XB, which is better than the interval estimate that you had before. So at least I can finish this and show you one picture and then just say one word to conclude maybe. So how do you build a high gain observer based on these ideas? Well, the way you build the high gain observer here, if you remember, the E matrix was just a chain of integrators. So we are completely disregarding in this design the original description of the nonlinearity phi. Okay, I will just use, you will see the matrices E, G, and F. Okay. So essentially, this is the formula. So if you are familiar with Khalil Eigen approach, the difference here is that you are not using the copy of the nonlinearity. The way you deal with the nonlinearity is that you assume that your phi function can be bound by an interval of some sort. And then essentially the way you propagate things is just like this. Essentially, if you go here, you can see that there is this trick that I just showed you using the positive and negative part. There is the propagation of the uncertainty in the initial state, and there is the propagation of this bound on the nonlinearity. So just to show you how this works, you see here there is a system that is not globally observable in the sense of the structure that I showed you in the first slide on this topic. But then you have some dynamics, you have some output from these dynamics, and you want to estimate this output and all its derivatives. So this actually you are measuring, so the upper bound and lower bound on the thing, on this quantity psi1, that is the estimate of zeta 1, all are coinciding. Then you go to psi2, that is the first derivative of psi1, psi3, that is the derivative of psi2, and so on, up to the fifth derivative. And you see that essentially when you run this observer on the successive derivatives, you are able to estimate them and to provide some bounds, red and green, which actually gives you an upper and lower bound, interval bound on each of these quantity, the measurement and all its derivatives up to the fifth one. So I think I'm essentially out of time. Okay. Okay, so I will stop here unless there is some question or.
Any question from the audience? For Sergio? Yeah. About the last talk, Sergio. So how the box depends on the gain. I guess that if you increase the gain, you can.
Okay. Okay, grazie. Yeah, okay, that's a good question. I will get you an answer from the author. I just received this yesterday, so let's try.
Just a comment that probably you may be in a situation that the volume of the box goes to zero, and this, not the volume of the box, the volume of whatever you propagate goes to zero, but the box actually gets bigger and bigger, so because they can get very thin. And so, yeah, perhaps with some polytopic arithmetic, so to speak, you can do a much better job.
Yeah, the point about the idea was to avoid going into smarter polytopes to try to avoid complication. I mean, if you have intervals, it's trivial to find where you are, to find, but that's true. I mean, in the scalar case, you increase the gain and this thing becomes smaller, but a scalar case is not really revealing because what you are suggesting is that you get stretched in one dimension again.
And in reality, people will do a particle filter for this. All right.
Thank you.
Any other question? Online, we are not taking
too much fields. Okay, so I think we can move to the next speaker.
Thank you.
Thank you, Sergio. I guess Luca does not need any presentation.
No, it's not true.
So it's a pleasure for me to introduce Luca Zaccaglian from University of Trento and LAS CNRS. The floor is yours. You have taken it already. So.
Thank you, David. Okay, so thanks everybody for attending. Today I'm going to talk about a specific activity that we did within this project that I'm especially happy about because it involves cooperation among two units, so with Alessandro Astolfi and also with Philip Brown from the Australian National University. And it is about revisiting an old problem with unicycles, where of course, many of us know that Alessandro is an expert. He's been doing seminal works in the 90s. And let's see if this works. Yes. So, and the idea is to have a unicycle dynamic. So I guess everybody knows this prototypical example, physically motivated, of a difficult nonlinear system where the dynamics H represented in Cartesian coordinates P1, P2, and phi being the orientation of this robot is affected by two inputs, U1 and U2. So if you have two wheels, input U1 would correspond to spinning the wheels at the same speed, and input U2 would correspond to spinning the wheels at opposite speed. So U2 changes the orientation, and U1 changes the forward motion. Now, the essential problem that one can address here is the parking problem. And the idea is to find a state feedback such that you get stability. So that means that if this state P1, P2, phi starts close to the origin, it remains close to the origin. And then global attractivity, which means that all solutions converge to the origin. Okay? So turns out it's a difficult problem. And so we know that Roger Brockett published in 1983 a paper saying that there exists no function u of x that gives you a selection of u solving this problem if you insist on this function being differentiable. And that later on, Eugene Ryan actually proved that you cannot even find a continuous function doing this. And so the problem is difficult in a sense because we know that continuity gives us robustness of the result. So of course there are discontinuous or time-varying solutions, but then it's difficult to prove intrinsic robustness. And that's actually what I write up here. Now, I could tell you a lot about many, many works that have been published about this, but then I guess Alessandro would be better off in doing that. But rather, I want to tell you that the philosophy of today's presentation is to take an idea from a 95 paper by Bicchi, Aicardi, and Casalino, and then Alessandro will correct me and say, no, this coordinate representation appeared earlier in 1983 from a paper by Butler. Was it Butler? Badreddin. The guy called Badreddin. But then, Riccardo, PhD students decided to cite this paper because it is very nicely presented. So if you guys want to read something old about this, I think this is a nice paper to read. And let me try to explain the idea. And now, today, really the message is, what the hell are we doing, And then somehow understand what is the real system and how does a coordinate system really represent a system or not. And the thing is that if you transform this state P1, P2, and phi, so again, P1 is the horizontal position, P2 is the vertical one, and phi is the orientation, okay? Now you can transform it into something which is r, beta, and alpha. So r is the distance to the origin. So this is the place you want to reach in the parking problem, okay? So r is the distance to the origin. Alpha is the heading error, okay? And beta is the orientation error. So you would like to park the robot facing right, okay? So these are the three coordinates that I'm going to be discussing today. I would really like you guys to think about them. I'm going to call them Z, okay? And by the way, at what time did I start? And how much time do I have?
20 minutes.
Okay, 20 more minutes. Oh, that's a lot. Thanks, Dad. Okay, so this coordinate transformation is weird. So if you want to determine x, so the original coordinates based on these coordinates, it's easy. And this function gamma is beautiful. Now, if you want to do the opposite thing, it's really tricky. And turns out that things are tricky at the origin, and you need to use this atan2 function. So you need to perform this transposed rotation, and then somehow, you know, p is p1, p2, by the way. So it's tricky, and let me remind you that atan2 is not a nice function. It's discontinuous in this set, okay? So this is not a nice transformation. It's actually discontinuous. And I should say that, you know, the other day we were discussing with Alessandro and Riccardo about some comments we got from reviewers for this paper which is submitted, and we figured out that in some existing papers, people use this atan2, and then they say, oh, you know, we have a continuous stabilizer, but then they didn't realize they had a discontinuity here. So they throw away the origin, but it's not a matter of the origin, like it's a whole, you know, half subspace. So that's tricky. So I get back to this rho, okay? And actually, I want to tell you that the philosophy of this work is to try to see what we can do by bringing a hybrid notion into this problem, and it will come back. So by the way, maybe I should be a bit more clear about the structure of my presentation. So I'm going to have a brief introduction first, and then I'm going to tell you a couple of issues that are resolved by hybrid, and then if I have time, I will discuss briefly robustness. Okay. So let me continue with the brief introduction, which is not so brief. Okay, so one thing that I'm not going to bother you with calculations, but that you can prove, is that if you take the original dynamics, x dot equals to h of xu, you can actually prove that the derivative of this coordinate z is fairly simple as a function of z. So remember, z is r alpha beta, and you see the right-hand side doesn't even depend on beta. Now, I'm using a transformed input v here because it's more convenient, but it's a very simple transformation, okay? Now, this 1 over r might scare you, but let me remind you that what that means is that if you know how to choose v, which is what's going to happen, then u is very nicely behaved because u1 will be rv1, and so what that means is just that u will vanish at the origin. So it's a nice input, okay? So remember, r is the radial distance. So, you know, you can prove all this stuff by, you know, doing some simple transformations, you know, with this type of things. Okay, so, so with these dynamics, I would like to emphasize that you apply Brockett's conditions, you know, these stabilizability conditions, and they do not hold anymore. That means this system is well behaved. So if you look at these dynamics, it is a very nicely behaved system. And so you don't have all those, you know, there doesn't exist a feedback, blah, blah, blah. Actually, there exists a very nice feedback which globally asymptotically stabilizes the origin. It's smooth, it's really nice. It's this black selection of V. And it turns out you can pre-multiply it by this matrix and you get a selection of U, giving you very nice trajectories of this unicycle. Because actually, so you transform coordinates, you select V, and you have U. You apply it to the system, okay? And so you have this nice theorem that says that if you choose these gains, Kr, K alpha, K beta, their meaning is clear. They are used to adjust the speed of convergence of each one of these quantities. So any positive selections will give you nice asymptotic convergence to the origin, global action. Okay, so the problem is solved. Okay, so there's nothing to do. And then we can apply U to the other system. Okay, kind of. And now, you know, this is the issue that I myself don't even understand completely as of yet. So we're looking at the z coordinates. What can we say about x? Right? Because actually we started from x. And then, you know, like you read all these papers and everything describes the unicycle with P1, P2, and phi, right? So one way you could think about that is let's take the dynamics of z and maybe already in closed loop with the stabilizer that I gave you because it's so nice, you know, and then it's parametric. You can adjust this gain Kr, K alpha, K beta. And then let's consider x as an output, because let me remind you that going from z to x is easy. It's the opposite thing which is hard. So x is very nicely defined. And then it turns out that this output does weird things. Of course, it's expected. Now, first of all, let me emphasize that this output has a norm which is essentially norm of p squared plus phi squared, as you see here. And then essentially, if you think about going back, you know, from here to the original z coordinates, you know, this is r squared, and phi squared is beta squared, because let me remind you, beta is minus phi. So the relation between beta and phi is really simple. So what this is z squared. Well, cool. Then, you know, z squared is larger than or equal to x squared. What that means is that a small z implies a small x. So remember, stability means start small, stay small. Now, I'm going to insist immediately on the fact that the opposite is not true, and I'm going to try to explain why in the next slide. But let me mention that, you know, if z goes to 0, because we proved the global asymptotic stability of this feedback, if z goes to 0, then also x goes to 0. So this proves global convergence of x. So the output converges globally to 0. Okay? Okay, so what about stability? Stability, no. Stability is a mess. So let me try to explain what you can do. You can build a sequence of initial conditions which is defective. You can build many of those. This is one possible selection. So say this is your target position. Okay, so this is the origin, and this red robot represents the place where you want to go. And you pick all of these initial conditions, say with 0. I know the speed is not in the model. So you pick all of these initial conditions. What you get in the z coordinates is this type of behavior. So r is smaller and smaller, and then alpha and beta, they all start at the same point. As you may see, beta has a uniform overshoot. Okay? So what that means is that you don't get stability because beta is equal to phi, right? And while in the original coordinates, the initial conditions are large because alpha is large, in the target coordinates, phi is 0 at the initial time, and the initial position gets smaller and smaller, right? So the norm of p is smaller and smaller. So I've built a set of initial conditions for which x is arbitrarily small at the initial time, but phi, which is equal to beta, always reaches a place which is far away. That proves that there's no stability. So the overshoot is uniform, even though the initial condition goes to 0. Now, why is this the case? If you ask Alessandro, then he will tell you, well, of course, because this is not a homeomorphism, you know, and then, you know, you see the trace of Isidori, you know, popping up of this, you know, sentence, which is hardly understandable for, you know, normal humans. But roughly speaking, what that means, so let me try to explain, is that if you take a neighborhood of the origin and you fix the orientation of a bunch of possible selections of the state of robots that are all facing to the right, so that phi is always 0 for all of these, then the norm of x is really the distance to the origin of all of these ones. But alpha, unfortunately, is large. You know, like in this case, it's pi. In this case, it's minus pi over 2. So you can build sequences converging to the origin for which alpha is constant and equal to pi. And so, you know, when you try to compute maybe the pre-image of the origin or whatever that would be, you will see that alpha is between minus pi and pi. So the origin in the x-coordinates maps back to any value of alpha. And you see this here too, because you see alpha is very large here. But you don't see these large sides of the initial condition in the x output. Or should I say the x-coordinates? So what is x? Is it a defective way of characterizing this unicycle? And then everybody's banging their head on the wall. Maybe Brockett's condition is about characterizing a system for which we chose really stupid coordinates and we should choose better ones, right? Maybe, we don't know. Anyway, so this is sort of the take-home message from the first part of my talk. And then how much time do I have? Sorry, see, it's like 10 minutes. Okay, very good. Okay, so again, you don't have stability on this output, right? But you do have attractivity. So how can we characterize attractivity? And let me try to explain a couple of things that will lead to hybrid. Now, before characterizing it, though, I want to tell you something that will lead to one extension. So if you look at this stabilizer K of Z that I showed you, sometimes it does really stupid things. Like, for example, if this is your target and you're in front of it, what it does is that it goes back and then it goes forward and finally parks. But it would make much more sense to just go negative speed and park, right? So why is that happening? It depends on the geometry of the problem. And so the idea is to use hybrid tools to switch between forward and reverse motion so that this is the behavior obtained from this initial condition. And that's really the big message of this hybrid thing that we do here. And so how do we do that? Let me go back to a slide that I showed you already, you know, when I defined this coordinate and remind you that alpha is the heading misalignment. Now, I would like you to think about alpha as a measurement coming from a camera, okay? So imagine that you have a camera in front of your robot with a certain field of view, okay? And then another camera at the back of the robot with another field of view. And then imagine now you choose, so there's some overlap in the field of view, okay? And this is quantified by a quantity delta that I will introduce shortly. And so imagine that if the target is here, and it's in the field of view of the front camera, you may, you know, just go forward and reach this point. But if the robot is here and the target is in the field of view of the backwards camera, you will, you know, do reverse motion. So that's the whole idea, okay? And how do we do that? Okay, so first of all, we duplicate the z coordinates, okay? So we have the front z and the back z. R is the same for all of them, but alpha f and alpha r are slightly different. And now what we can do is we can redo all the calculations we did before, but with the caveat that the camera is in the back. So there's typically a pi difference in the alpha betas that you can work out pretty easily. And the interesting thing is that the transformation that you need to do from x, you know, the one that was ugly with atom 2, now becomes very nice because it involves a difference of sign, and it turns out within the field of view of the camera, you completely cut out and throw away the discontinuity of atom 2. So we were able to completely pull out of the picture the discontinuous part of this ugly function, and so now everything is smooth relative to the domain of existence of these angles, okay? And so hopefully this will be clear in a sec. Now, so then what you can do is you can define not only rho, but also gammas. Gammas will be very similar to before. Gamma was the easy function, as you guys know. And this also shows you that between R and F coordinates, there's a pi difference, as I was mentioning before. So when you switch among the two, you will see something like that. Okay, so what can we prove based on what we already proved when we were just looking at the z coordinates? Same exact thing. So you can get, you know, global asymptotic stability of the origin when you only use the front camera for any choice of the three gains, and also, you know, from the rear camera. So of course the stabilizer is slightly different because you have these green things. You see they have opposite signs. That actually is telling you in one of them you have forward motion, in one of them you have backwards motion. Okay, it's not totally true. I mean, there's a mixture of them, but you see the change of sign here. And so now what we can do is we can go beyond this and really get to the core achievement of hybrid, which is that the angles are actually limited. So the camera's angles are limited, but also the beta angle is limited, something that I haven't insisted on or I haven't discussed so far, and that I would like to discuss now. So you cannot choose a large angle like 100 pi. It means the robot would spin on itself uselessly, right? So we would really like to restrict the domain in a bounded set. So for example, like minus pi pi, it will be a slightly larger one. And then we will reset these angles when it is time to do so. So this is illustrated here, like if you have this orientation, this is a certain beta, but it could be also 2 pi minus beta. So 2 pi jumps are essentially no jumps. But mathematically, we have to implement that. OK. So, and then with respect to alpha, as you see, I think I'm going to go fast here, but the rough idea is that if you have a certain camera and you reach, so let me actually concentrate on this. So alpha will belong to this interval, you know, from minus pi over 2 plus delta to plus pi over 2 plus delta. It's a bit more than pi over 2. And then when you reach the boundary of this set, you reset. And the way you reset is you really have pi jumps when you go to the other camera. So you switch from alpha f to alpha r, front rear, and vice versa. Does that make sense? So it's a very natural jump. OK, hopefully it's clear. And for beta, it's even a much more simple reset logic. For technical reasons of the proofs, you actually, a preferred thing is to insist on beta belonging to this set, you know, like 3 over 2 pi minus delta, minus 3 over 2 pi minus delta, 3 over 2 pi plus delta. So beta is never larger than a bit more than 3/4 of a circle. It doesn't matter. I mean, you can change that, and probably there's ways to extend this. OK. And so whenever you reach this boundary, you reset beta. So let me try to put all this together. And to do that, I'm going to do what we do a lot of times with hybrid systems. We introduce a logic variable, which becomes a state. And this state is either -1 or 1. 1 means we're using the front camera. -1 means we're using the rear camera. And then we add q to the state z. But remember that now alpha and beta can be alpha front or alpha rear, depending on what q is. So everything is clean now. Okay? And then the dynamics, it looks ugly, but it's just a collection of what I told you already. So you remember the green terms where we had minus or plus v1? Well, we put q, right? Because in one case you have q equals 1, or in the other case you have q is -1. Then the feedback stabilizer also had a plus minus here that probably I didn't discuss enough, but it's really simple, right? Same type of mechanism. And then, you know, solutions are not supposed to switch cameras or angles as long as alpha is in its range and beta is in its range. So this set is bounded in the alpha beta direction. And then there are two jump rules, the discrete time evolution of our model, and these are triggered when you reach the boundaries of this set. So you trigger a jump of alpha when alpha is at the boundary, and when alpha jumps, you switch the camera, and of course you update alpha to the other one. And when there's an orientation rest, that means beta is at the boundary, and so you don't touch the rest, and you just unwind the beta. Okay? So with this model, which is a perfectly clear hybrid model, and by the way, I would like to mention that the jump set is the boundary of the flow set, which is very typical with certain hybrid systems, so that solutions will be defined for arbitrarily large time, because when they reach the boundary of this flow set, they can jump, and you can prove they jump to the interior of the flow set when they do this. Then we can prove this nice theorem. You know, you can gather all these dynamics in this overall description, and you get that for any delta, so delta is this margin that you may choose between 0 and pi over 2, and for any selection of these gains, you have this stability, like you stabilize to 0 R, alpha, and beta. Q, of course, will be switching. And there's another nice result that you can do is you can impose K beta equals 0 in such a way that you only stabilize the position and you don't care about the orientation of the robot. And you can do that, and it's characterized by this set. So the position is 0, the orientation is any value. Okay? And so that's the main result. It's fairly clean. Let me show you some simulations. So now this was the bad initial condition, or almost such. You see it goes backwards and it reaches the origin. Okay? So you see red and blue based on the value of Q. And in this case, we stabilize with the positive K beta so that everything goes to 0. But in this case, we get K beta equals to 0. And so you see you have a generic orientation beta. And the trajectories, of course, are, say, simpler, intuitively speaking. OK. And then I need to be done, right? So I wanted to discuss robustness. So maybe I should tell you that you can prove uniform convergence of the x coordinates. And I wanted to discuss robustness because that's what you get for free from the smooth selection of the hybrid stabilizer. So everything is super nice and clean if you do it in the z coordinate. So you get robustness to very, very large types of variation. So you can perturb the right-hand side any way you want. But when you go back to the x coordinates, you keep having this problem of how do I match it up? And there are issues, and this slide is very ugly and technical, so I'm just going to skip it. Also because I'm not sure this is the right way to look at the problem, to think about perturbations of the x dynamics and how I can relate them to my result. So I guess I'm going to just conclude and say that, besides what we did, what are the real coordinates? I can put the cameras on my robot and just say x does not exist. It's just z, right? So then where's Brocket? I don't know. Or should we say something about that? Is it interesting? Or should we just say that the problem is solved in the z coordinates and who cares about x? Just trash all the papers by Astolfi in '95 because they're useless, right? Or but maybe no, maybe it's important. Maybe it's important to look at the x coordinates because closer and closer to the origin, you cannot spin your steering wheel super fast, right? Maybe that's the issue, and it's a real issue. And then it would be nice to have experimental results with onboard sensors to see what happens. And thanks for your attention. Okay. Sorry for being late.
No. Thank you. We have a question from the audience. One.
Nicola.
I think that everybody can speak.
No.
Okay.
We are online.
Okay, sorry. Thank you, Luca, for this nice presentation. So I'm just curious to ask you if the problem of the inversion of tangent function R tan2 can be solved through the SO2 or SO3 manifold. Instead of, let's say, trying to find the angle, why don't you stay on the matrix? And this is a curiosity, clearly. I guess that you've been working on this so long, you know the answer. And the second curiosity is about the final result. So you shown us that the beta remains always, let's say, with a certain overshoot despite initial conditions now. At the end of the day, you told that you have this global acceptable stability properties. Isn't something which is in, let's say, contrast with what you said before? Or did I miss something?
So I'm going to first answer the first question. And yes, you can focus on SO2, but the problem is that you will need a coordinate system eventually. And so you will fall back into the same issues, right? So I think we're like now trying to address the problem of the feedback. So when you do the feedback, you have to take some quantities, and the intrinsic problem is still there. I don't know if it's clear. So you would need to cover SO2 with some local mappings. And if you think about it that way, that's exactly what we do. The front and rear camera are two charts that will cover the whole angular space in a proper way. But then again, sometimes that language is very hard. If you talk to Davide, he will perfectly understand all the details. If you talk to me, I have some issues. But then the second question I didn't understand. Sorry, you went too fast.
Yeah, sorry. No, you were showing us that the beta has an overshoot, which is like uniform with respect to the initial conditions, isn't it? Okay. And you said that actually you can have the stability, no? But the final result was about GAS, which is stability.
Right. So these are the x coordinates. So this does not disprove stability in the z coordinates because alpha is large. But in the x coordinates, r is p squared, and for all of these cases, phi is 0.
Okay.
Right? So
okay. So just
And by the way, this
Did you
is
get the point?
stability. It's not. This is like not really what I would call stability because the dynamics is in the z coordinates. The feedback is in the z coordinates. So we're sort of looking at an output. So this would be a property that looks like output stability. The one that has been defined by Politecnico and co-authors, where you try to prove a delta epsilon bound on an output of the system, and it turns out this is clearly not possible. So hopefully, I know that there's a mixture of different coordinates here, so it's a bit confused.
okay. So sorry, just my fault. Okay, thank you.
Alessandro maybe has something to add.
So to observation, so SO2 is not isomorphic to R whatever. So there is a theorem of Whitney that will tell you that you cannot have a global equilibrium, asymptotically stable equilibrium in something that is not diffeomorphic to Rn. And so if you go to SO2, you will have another equilibrium, which is typically what like the top of the sphere and the bottom of the sphere. The issue here is that as you go from the Cartesian coordinate to the polar coordinates, you don't map neighbors of the origin into neighbors of the origin, and your open loop system becomes discontinuous, so Broca's theorem doesn't work anymore. And not even Ryan's theorem, because in principle you require at least a C0 vector field. And so essentially that's it. So there's no contradiction with Broca's theorem because this is an hybrid feedback, and in a certain sense it's still fine. So that is not the class of feedback that Broca was considering. And keep in mind that the proof of Broca's theorem is a topological proof, so continuity is sufficient for all of this. So the hybrid structure removes this continuity out.
Okay, so thank you. I don't want to discuss about what your result.
No, but the whole problem.
Okay, thank you.
Yeah, thanks, Alessandro. Thanks, Nicola.
So everything works, if I understood correctly, because you have a nice x to z transformation and a nice v to u transformation, right? So you can implement in the u coordinates something that has been designed in the z coordinates.
Yeah.
So have you thought about a possible class of systems that have this nice transformation in the state in one direction and the inverse transformation just in the u? Because actually probably it's much larger, the class of systems, nonlinear system, for which you can apply this kind of trick.
I haven't talked about it. I fully understand what you say. I totally agree. It's a fairly interesting thing, and if you have some insight, it would be nice to discuss. But there's one thing also that I would like to bring up. Once we focus on Z, what is the role of X at that point? Because what's important here is U.
Yes,
So for me, the philosophical question is, if I am very happy with this representation with R, alpha, and beta, why should I worry about Cartesian coordinates
Yes,
and an orientation which is once again in an angular orientation, so it has all of these issues that Alessandro was mentioning, right? And yeah, and I think, you know, this class of systems can be much larger, and I think tools like this would be relevant in addressing things that we're looking into with Davide too, stabilization of drones, where you have this issue with the zero thrust, which characterizes the condition under which you really need to flip the drone and do something else. And situations like that where you need to change your mind because you know, you need to unwind the angles or stuff like that. And maybe you know, maybe that's something we could discuss. You know, that you have in mind a larger class, possibly going in the UAV direction or something similar.
Thanks. Questions? No? Okay.
Thank you, guys.
Okay, I've picked the microphone because it's my pleasure to introduce the next speaker, who is Nicola Mimmo from University of Bologna.
Aspetta, guarda, questo in tasca. E la cosa migliore è metterlo qui sulla camicia. No, forse sulla giacca. Grazie, non può parlare.
Prova. Grazie.
Well, it is my pleasure because the topic he will talk about is super interesting, and that's not related to the fact that my name is on the wall.
Okay. So yeah, before starting, I'd like to thank both the steer guys that organized the workshop. So thank you very much for inviting us, and thank you, Lorenzo, for inviting me as a consequence of this. So differently from the previous authors, which are, as you said, is also much more expert than me. Today this presentation will be without any equation, so that you can enjoy pictures, okay, colors and something like that. Since I actually knew that there will be, let's say, a young folk here, actually I didn't, but I prepared this presentation like this, okay? So I hope you enjoy this. We approach this problem by a very robotic perspective point of view. Clearly, if you go on the paper that fortunately we have published in the next CDC, you find all the mathematical details, okay, guys? So if you are totally crazy, you want to read it, yeah, that's if you find the reference there, okay? Okay, so let me just this, okay. So the talk is organized in this way. First of all, I'd like to motivate why we have investigated this topic. Sorry, one step back. Clearly, this work has been made by me and Giulia Micheletto and Angelo Cinese from University of Padova, also with the help of Roberto Naldi, another colleague of mine in Bologna. So the talk has been organized in this way. So I would like to motivate why we are doing this work, and that's important to let you understand that, let's see, his previously mentioned also we have been working on this topic for several years, thanks to the project where we won in the past. And then we would like to address this problem in a different way, which haven't been investigated before. Then we'd like to show you which is our philosophy to solve this problem and how to make this working in practice. And then some simulation results, because we are still waiting for the drone to be ready, okay? And we go to the conclusions. Okay, so just aim what we are doing inside the project, the DOCEAT project. Those are the goals we declared on the proposal. Okay, they're very ambitious, and it's actually what I'd like to mention is that we were looking for drone of the future platform. Okay, so what we want to do to have these things working in reality. Okay, so among these objectives, the first one was trying to make a fleet of drones working together to do something. Okay, so this work is fit into this first objective. Okay, So maybe clearly before they were talking about resistance to faults, to sensors, which is inside one of the topic here, I guess, fault tolerance, the third, and so on and so forth. Okay, so but that's our goal. And in particular, we want to exploit drones to do something to help rescuers in avalanche scenarios. So as you know, I mean, avalanches are a natural phenomena, but most of the times are triggered by irresponsible behavior of humans. Okay, so what happens is that after you get buried by the avalanche, so your temperature goes down, and then hypothermia comes very fast. And what we need to do is to, if you are lucky and somebody knows that you are there, calls the rescuers, okay? So they need time to get to the place, and they organize the rescue operations, and then they start, okay? So all this takes time. And after 15 minutes of burial, you have like 5% of possibility of being, or survive of the avalanche events, okay? So that's why we need to be super fast, at least when we get to the place. So from that moment, we assume the rescuers are equipped with our fantastic drones, and the drones are trying to help to reduce the time to rescue, to find the place of burial. That is our goal, okay? So how can we do that? Basically, we rely on some technology, and this technology is called ARPA. ARPA is like an acronym from Italian, this transceiver, avalanche transceiver, okay? And this is made of two elements. So there is a transmitter, which is active, and a receiver. So everybody wear this device in a transmitter mode, okay? And when something happens into the avalanche, so the rescuers switch the device into receiver mode, okay? So actually this actual system is propagating this electromagnetic field over the air, and you receive it thanks to your device, okay? So what we receive on the those devices here is actually a couple of informations like the intensity of the field and the direction of the field, okay? So thanks to these two information, several algorithms to find the burial place have been developed over years. And in particular, we have been working on this. I mean, first of all is, okay, if I follow the flux lines, at the end of the day, I will get to the transmitter, okay? But as you can see here, I mean, if you are very unlucky, you start here, maybe you have a path which is super long, okay? You get lost. And if you go on this direction and you want to go back, you need to switch in logic that makes everything working properly, so it's not easy. Or what you can do is to scan the area of the avalanche site and find where the intensity is the highest, but also this takes time, okay? Then we also tested in the past what is the called source seeking. So if I know that the power I receive will be reduced if I get far from the transmitter, what I can look for is the maximum intensity of these signals, no? So I just look for a little bit around me, and I find the direction in which this power is increasing. And also, in the past, we used this concept of, okay, if the radiation pattern is known some way, okay, I can employ that model into an observer, or an estimator that estimates the parameters of this, in which we have also the location of the burial. And that's, let's say, easy. We can also find the solution in that way. In particular, so in this work, we are still in this online estimation, okay? But we are mixing things. In particular, we are mixing source seeking and online estimation, okay? So we are trying to do something better. They will see it finally in the simulation results that, let's say, the joint work of these two algorithms can provide better results in terms of time or reduction of time to find the victim of the avalanche. Okay,
So that is the problem description. I mean, what I think is my scenario, I have one single transmitter, one single person under the avalanche. Then I have several transmitters, which are, let's say, equipping my drones. Okay? And what I can do is to move the receivers. Then, possibly, I would like to deploy on this fleet of drones, a control low, that move them in order to estimate as fast as I can the location of the victim of the avalanche. Okay. So clearly, as Luca mentioned before, also we are targeting to something which is not getting us exploding if we start close, and maybe possibly all the trajectory goes in the right way, in the, let's say, uniform way. Both the trajectory of the estimator and the trajectories of the drones must go into, or to converge into an area. Okay? So then this is where our work, mixed work, comes into. We decided to mix our approaches. From the University of Padova, they know exactly what is the bearing-based target localization. And here in Bologna, we know actually how to work with ATWA, okay, and how to perform experiment seekings. And so that's why we mixed it together, these two work. So the idea is simple. Let's start with the transmitter located somewhere in the inertial space. This is P of transmitter. And then we have a fleet of drones, okay? So I assume that I know where I am with every single RX. And let me define this vector, which is the bearing vector, so the direction from me to the transmitter for each of the agents, okay? So as Giulia and Angelo can teach us, actually the resolution is this. I mean, I get the stack of all the directions, and I look for, in my problem, the point that matches all these directions, okay? It's like in this minimization problem, you take this guy, you move it in your minimization, and you find a position such that all the directions are aligned at the measurement you have, okay? So that is the working principle. So guys, I think that you will not be happy about that. Could you tell me why? Okay, let's see. We have three main issues with this. The first one is we don't know actually the directions, okay? There's no way for me to know where the transmitter is, so I don't know where is the direction for me to that, first. Okay, second, this solution, even if we assume we have the bearing, okay, this solution is subject, is ill-conditioned. It depends on the scenario. So as example, if I am very far from the transmitter, and this is something that happens always, because when the rescues approach the avalanche site, it goes from the bottom, okay? And the avalanche goes from the up, from the bottom, from the top, sorry. So you start scanning from the bottom like this, and probably the victim is somewhere there. So this scenario in which I have the transmitter far from, it's absolutely possible, it's possible. And then what happens is this. Actually, though all the directions comes very parallel to each other, you know, it's very hard to find a solution to this problem. And probably, possibly, what happens is that your estimation is quite wrong, okay? So the third one is that actually there's no way to solve this problem. We need to solve it numerically, okay? Because it's a high nonlinear problem, and there's no way to find it in a closed form, generically, okay? So what we do usually is to approximate this solution in some way. So now we need to deal with all these three problems in order to make this system to work in reality. Okay. Problem one. The problem one was about the existence of the knowledge of the bearing directions. So let's assume this is my formation, and this is the transmitter, and the power which is emitted by this has some ISO power lines, okay? So as far as you move away from the transmitter, the power goes down. And usually this happens with the, let's say, inverse of the cube at a distance lower, okay? It's quite normal. And then what I can do is, okay, wait a second. If I take my position and I perturb this position like in a circle, okay, what I can do is to sense the variation of the power along this circle, okay? So usually then I collect data from the, let's see, only for the analysis, graphical analysis of this, let me assume I have, I know the power at the center of the circle, but actually it's not needed in reality, okay? So what happens is this, I take this map, I continue sensing the power on the circle, and I have this output over time, okay? This is the output of my power with a bias. And I have here projected my position in space along the circle like this, okay? So if I multiply these two signals together, for sure they have a synchronization, okay? So the extremum seeking theory tells me that if I take the average of this signal here, then this corresponds to the direction along which the power increases, okay? So good, it means that I have to move my system along this direction to increase the power. So we can do the same also for the x component, for the horizontal one, and get a final direction along which should I move my drone in order to increase the power. So that is the basic of the extremum seeking concept, which is actually what we have done in the past, okay? When I mentioned the method we used. Okay, the source seeking. Good. So clearly the extremum seeking is providing you something which is an approximation of the direction in which, along which the gradient, the power increases. So we have an extra error in this. And absolutely, guys, this delta I, which is the right gradient, is not related to the bearing at all. Okay, it's another measurement. So actually, the best we can do at the moment is to use this hat delta, the estimated delta, instead of the B, the bearing we had before. Okay, so this is indeed an approximation of our directions. We can do the same for all the drones. And then we have all these delta available. Then we use the stack of the delta inside the original problem and define again the same problem. Okay? So what we look for is something which is a friend. It's not exactly the real PT, but it's a friend of that. So what you can see here is that if I assume the iso power lines isotropic, I mean circles, okay, all of them will converge to the right PT, okay? So indeed, the shape of the deviation pattern has a big impact on this solution, okay? We can be close or far from the target depending on the shape of this pattern. So we can do now a second step to make our solution better than before, understanding what happens if my transmitter is very far from us. And then let's assume that this is the configuration, and let's assume that the PET is this one, okay? So even if I have an error in that one, possibly what I can do is to exploit this information. So the victim is died, okay? Okay, so to move maybe the wall formation, okay? And say, okay, I have a formation here, the transmitter is there. What I can do is to get closer. Because if I get closer, what happens is this, okay? So we move with a certain intensity, okay? And if I get closer, what happens is this. I mean, you see all the blue arrows, which is the new bearing of my system, are indeed more orthogonal than before. And then the problem will be more robust, okay? So if I do this again and again and again, at the end of the day, I will circle, I will surround the target, okay? So it's just a matter of time, and I will get there. And once I get there, the bearing direction is so orthogonal that everything works as we expect. Okay? So this is for the conclusion of that. But we can also do this once again with another source, which is the extremum seeking source. Okay? So indeed, what happened is this. At the beginning, I start seeking for this gradients estimation. Then I use exactly those directions in order to move the formation. Indeed, what happened is this. I collect these vectors. I just compose them to move the drone fleet. And I get closer to the transmitter. Okay? So as you can see, I mean, right now I'm getting closer. And next step will be closer and closer, until, again, I surround the formation. So the question is, why don't we solve the problem by external seeking only? I mean, it seems that I can do that. Actually, guys, because external seeking is very, very slow. Okay, so you need time. You need time to circle and collect the measurement and compute the average. Okay, but we need to speed up the search because we don't want people die. So this approach is, I mean, super. It's a baseline. It's a good baseline, but it's too slow. We can't use this only. So that's why we want to rely instead of the good performance of the estimator or the position in order to speed up the search procedure. Okay, so for what about for the recursive estimation of our PT, as I said, we can solve this in a closed form. So what we can do usually, or I mean, as they taught me, okay, usually we compute the gradient of the function and we, let's see, numerically go through the gradient descent. Okay, so but as you can see, I mean, in order to get to the final point, I need like an infinite number of steps. Okay, asymptotically it converges to that point. But in practice, I can't wait for an infinite number of steps in my computer. Then I have to stop my execution after a certain number of steps. Okay, so this introduces an error, which we also took into account in our analysis. Okay, okay. So now all the ingredients are ready, and this is our proposal for solving this problem. So let's investigate it step by step. In the first part of our argument, we have all the agents which are shaking in order to estimate these gradients. Okay, so then we collect all the gradients, and we have a central unit, okay, which is collecting these gradients and which is running this least squares, this recursive estimator with a gradient. Okay, so after a while, this machinery provides me the estimated PT, and I use this estimated PT to move the formation. Okay, so now what is the concept inside here? As I said to you before, I can steer the formation by means of two informations, like PT minus P center of formation, or the direction given by the experiment seeking. So the idea is this one. We want to mix them and use them properly when my PT is not, my estimation of PT is not reliable. I mean, if it is not reliable, I rely on the experiment seeking, okay? And meanwhile, I get closer and closer. Once I get sufficiently close that the PT is good, then I rely on that one, because much better than my experiment seeking, okay? So that is the concept which is behind this rho factor, which is indeed mixing these two sources of movement. Okay, and actually, okay, this is maybe the only formula I reported here to let you understand what is happening. So I'm updating the formation like where I was before, plus a balance of these two directions, okay? So now what we have to do to complete everything is this. Okay, first, we decided to implement this like a discrete time system, okay? So something happened, then something other happened. Okay, so we need to decide which happened when. Okay, what happened when. And in particular, what we decided is this. So this inner element here runs at every time step. Okay? So at every time step, it updates the estimation of PT. Okay? So clearly, at a certain moment, I need to provide the vector of my gradients estimation, this to the recursive least square. Then it runs, and meanwhile the formation stays still. Okay, it doesn't move. But all these time steps, it doesn't move. So we have defined a certain interval, like capital N, which is the number of steps that this estimator can take. After that, we decide to both move the formation and send to the RLS the new update of my gradients, okay? So the extremum seeking is continuously working, okay? It is continuously estimating the gradient, okay? I have a continuous flux of information from the extremum seeking. These delta are available at every time step, but I do not use them always, okay? So I shake the drones while I move the formation. In the meanwhile, at any time I change the formation location, then I run the recursive least squares. And that is our approach. So why we have done this? I mean, is there any sense? Well, why? The reason is this one. So first of all, we need the algorithm to converge somewhere. So the recursive least squares to converge somewhere to estimate the PT, okay? And then meanwhile, in that algorithm, I can't change the data. They must be the same. So that's why I provide the data to this guy only once at any n steps. Second, the basic working principle of the extremum seeking is this. As soon as I, let's say, stay still and I circle around a point, it provides me very good estimation. But because there is a correlation between the power that varies and the movement of the drone. But if I move the drone too fast, I mean, things are much more confused. And the algorithm can't provide you a good estimation of the gradient. So that's why we need to separate the dynamics of these two. The dynamics of the extremum seeking, the shaking frequency, and the movement of the formation. Then we have done this by means of this gamma. Indeed, gamma will be defined sufficiently small. I mean, with design sufficiently small. In order to let the drone shake sufficiently fast and faster than the movement of the formation, okay? And also n, which is our, let's say, the number of steps we take before updating the formation. Also, this guy needs time to get to sufficiently close to the solution, okay? So this is like a two time scale separation. One for making the recursive least squares work. The second one to make the extremum seeking to work, okay? So gamma small and large. That is the design philosophy we have. And clearly this has been defined in this way because we know from theory that from timescale separations we have dynamics which are sufficiently good in this time scale, different time scales. Possibly everything works at the end, okay? So let me show you the simulation results. And let's, at the beginning, let's stay focused on the extremum seeking only here, the mid part. So this is like set my row function to stay always to 1. Okay, let me remember. To 0, sorry. So I'm just using the extremum seeking, okay? So I'm shaking the agent while I'm moving them accordingly with the direction I'm getting from the formation, okay? From the extremum seeking only. As you can see, at the end of the day, probably it will converge, okay? It is going, the red dot are the estimation, and the formation is steered by the estimation. You see, this is probably going there, okay? But it takes very long time, okay? We can't wait for that long. What happens if I use just the approach based on the recursive least squares without the extremum seeking into the formation movement? So what happens is this. I mean, there is some initial phases in which the estimation is so uncertain, then the estimation of PT is also uncertain. Then the formation starts moving randomly somewhere, and then at the end of the day, it goes back to the right direction, okay? So it goes, you see that we estimate correctly the position of transmitter, probably once we are sufficiently close to the transmitter itself, okay? But if we combine the two things, the two approaches as we've done, you see that actually there's a much more uncertainty in the middle. So the formation goes straight to the transmitter location. So this is actually what we were looking for, no? The improvement of the performance of the search time. Okay, so that is the end of my presentation. And just to conclude, I would like to recap you which are the main steps we took. First one, we started from two elements, like the extreme shaking on one end. On the one end, there was the recursive least squares, okay, the estimation made of the bearing, on the bearing. Then we mixed them, and we discovered that we can take advantage of these two by a certain logic which is based on the timescale separations. Okay, so now the next step will be, okay, first of all, we need to conclude the proof of stability, which is not already ready, okay, but don't worry. You will not find it on the CDC paper, okay? And the idea is this one. Wait a second, but, okay, the art one maybe is simpler, it's too simple case, okay? And it's simpler than reality. The reality could be I have any radiation pattern like this one, okay? In this radiation pattern, I have some directions with 0 power, okay? So differently from the ARTWA, which was like ellipsoids, and the power is spread everywhere. In this last one, there are some directions which I have no power. So when I move my formation, probably I don't want to make drones to stay where I have no power. So there's also important now to, let's say, move the agent relative each other in order to create a new formation like this. I want to change it. And to place the agent in the best locations in order to estimate transmitter position. Okay? So actually, this is an open problem. We still don't know how to. Okay? We have a good idea on how to solve the problem, but still working on that. Okay? So, and thank you very much for the attention. And if you have any question, I'm happy to answer.
Nicola, is there any question or comment for the speaker?
I have a question.
Sure.
Thanks, Nicola, for the nice presentation. Thanks for the nice presentation. I was just curious, you know, going back really to the origin of your problem statement. I guess what makes your optimization problem hard is this normalization that you have, right? In these vectors. I just wonder what happens if you don't normalize, or at least you just multiply by the norm so that B will contain P again, and then it becomes a quadratic program, I suppose, right? Does it work, or like it gives even crazier solutions?
So thanks for the question, Luca. It's absolutely my pleasure to introduce Angelo and Giulia, which are the master of this.
I will try to answer to this. In this case, you have bearing measurement that is decoupled from the distance measurement. In the other case, you will have bearing and distance that are mixed. So actually, using bearing, you are moving transversally with respect to the target. So for one example is the case of the lobes. In the case of lobe, you have to move transversally in order to maximize the power that you receive. And then you can reduce the distance by increasing the power. So if you mix things, you may have that you are not actually going in one specific direction in order to minimize the problem, but you can end up in some weird loops where you are maximizing and minimizing the power. I think this is so just abruptly one answer that I can give you.
Any other question or comment? Okay, let's thank Nicola again. So this talk concludes the first part of the talks for the morning. Now we have a small coffee break. Right? Okay. Qual è il problema?
Okay. Thank you again for being here. It's a pleasure to introduce Giulia Micheletto, which co-organized with me this workshop. you kept me on schedule, so thank you. Thank you.
A time garden.
The floor is yours.
Thank you, Davide. So it's a pleasure for me to be here today, and what I want to present is something related to the concept of maneuverability, and specifically maneuverability of star-shaped tilt Hexarotor. This is actually a joint work with a lot of colleagues. One of them is sitting here, is Angelo Cenedese. And this is a work that dates back a couple of years. But I think it is interesting in the context of our DOCEAT PRIN. Well, what is the maneuverability? What we intend with this word? And to have an answer, I put this question on ChatGPT, and I say, okay, what is maneuverability of a multirotor? And actually, he, she, it answer me saying that is a capability related to the fact that a drone can perform some movement in terms of translation and rotation, and it can do it in an efficiently and precise way. And specifically, he, she, it, I don't know what ChatGPT is, well, but he highlighted the fact that maneuverability is closely related to the rotor configuration of our platform. And why we want to study this property? Because as our project PI said before, nowadays drones are no more passive elements in the environment. So we don't use drones only for surveillance tasks, but we want to use it also for some physical interactive tasks. So we want some more capability in terms of actuation and in terms of movement they can perform. So, well, my presentation is actually divided in three parts. The first one is the part 0, so some preliminary. I want to provide you some model and some mathematical element to characterize better to having a model of this platform. So, as I said, the focus is on star-shaped tilt Hexarotor. I will use the acronym STH to indicate this platform. So, in detail, what it is an Hexarotor, and that's quite clear for everyone. So, it has 6 propellers. It is a star shape, meaning that these propellers are evenly spaced on a circumference, so they are placed in the vertex of a regular hexagon. And with L, we indicate the length of the arm. And so we have this equation here, yes, to indicate the position. Then they are tilted. So they spin around an axis that are actually not orthogonal to the plane where they are placed, but they could be generically oriented. So in particular, we made some assumption. We divide, or better, we distinguish between 2 angles, the cant angle and the dihedral angle. The cant angle, we call it alpha, is the angle around which we tilt on the direction of the arm, okay? And specifically, we assume that consecutive propellers are alternative tilt. So we have a couple of propellers like this, the consecutive like this, and the others like this, okay? The other assumption is that we pick a dihedral angle equal to all the propellers, meaning that they are all equally tilted inward or outward, okay? With FB, we indicate the body frame, so the frame that is associated to our platform and is placed in the center of mass of our platform. Everything is clear right now? Okay, very simple. As you know, we have an actuation model linked to this platform. So each propeller is able to exert a torque, thrust force, a drag torque, and also a thrust torque. And all of these quantities are related to the input that, in our case, our control input is actually the spinning rate of the propeller at the power 2, so the square, okay? If we put all the elements, the force and the moment element in a symmetry, so we take all the contribution, we have that in the center of mass of our platform, we have a control force and a control moment. And you can see by this equation, that depends on this Z which is actually the spinning axis of the propeller. So the direction of the control force and the control moment depends on the single direction of the spinning axis of the propeller. Well, let's move on. Let's introduce a control input vector. So we stack in a single vector all the input of our propeller, and we assume that those are limited because we have some physical constraints, we have some limitation given by the motor power, okay? And in doing this, we can express our control force and control moment as the product of a matrix and a vector. In particular, we have two important metrics that are such control force input matrix and control torque input matrix, and that depends on the two angles I mentioned before. So alpha, the cant angle, and beta, the dihedral angle. In particular, those two metrics are 3 times 6 metrics, so these are rectangular, and the columns, each column is related to one of the propeller. As you can see, again, we have the Z. So the columns of such matrix depends on the orientation of our propeller. Okay? Well, something more. We introduce the word frame, so the inertial frame, which is fixed. We can indicate this framework with a FW, and we assume that the axis of this frame corresponds to the canonical vector of the R3 space. And we can describe the dynamics of our platform as a standard dynamics of a 3D body in the space. So we have the translational equation and the rotational one. And as you can see, the rotational dynamics depends on the force, the rotational dynamics depends on the torque. Let's substitute the expression of the force and the torque with the matrix product that we have introduced in the previous slide. And here we are. So in CDC 2019, we have presented a paper on which we have explored this kind of platform, and specifically we focus on the rank of the F matrix and M matrix. That I recall you, F is the control force input matrix, and M is the control torque input matrix, control moment input matrix. And well, the first matrix could have rank equal to 1 if we have that the two angles are equal to 0. Meaning that we are accounting for a standard platform on which we have coplanar and collinear rotors, okay? If we tilt our propeller in some direction, we have that this matrix here, F, become a full rank matrix, while M is always a full rank matrix, meaning that we always have fully orientation actuation. And the fact that all matrices having the two terms, that is actually a 6 by 6 matrix, has full rank, so equal to 6, tell us that the platform is fully actuated. So the platform is fully actuated if we pick one of the two angles different from 0. Okay? Okay. As I said, full orientation actuation, while for the force we can have a different situation. Let's introduce two auxiliary metrics. Some mathematical detail, but try to follow me on the reasoning. We have those two auxiliary metrics. The first one corresponds to the image of the transpose of the M matrix. The second one corresponds to the kernel of the M matrix. So basically, the B matrix describes the kernel of the control input matrix. So it describes the input that guarantees us 0 moment. Okay? While the A matrix is such that the two space generated by the columns of the A and B matrix are actually orthogonal. So we can decompose our control input into as the sum of two terms. The first one is UA and the second one is UB. And both of them belongs to two different space. But what is interesting is how the composition reflect in terms of force. we have a decomposition of the force. The first one, Fa, depends on UA. The second one, Fb, depends on UB. And so we can distinguish between three different force space. The first one is F, the total space of the force, okay, the control force. Then we have these two space here. Let's call it Fa and Fb, and corresponds to the true component according to this decomposition. Okay, so roughly speaking, what are the spaces? The first one, as I said, is the control force space, all the force you can generate with in your platform, okay? The second one is what we have called spurious control force, because if you generate a moment, you have the emergence of a force, and this force is inside this set. The third one is the most interesting one, that is the zero moment control force. So the force that associates to a zero moment, that allows you to have zero moment at the end, okay? Another previous results tell us that a platform is fully decoupled in terms of force and torque, meaning that you can apply independently a force and a torque if you pick an angle, alpha and beta, inside our interval, okay? So either if the angle is equal to 0, the platform is actually fully decoupled, even if it is not fully actuated. So it could be fully decoupled, but not fully actuated. On one side, we are talking about the possible movement. On the other side, we are talking about the dependency between the force and the torque. Well, let's move back to the concept of maneuverability, because we have introduced all these concepts for a reason, of course. So, as I said, ChatGPT tells us maneuverability is related to the fact that you can do some movement. What is maneuverability for us? For us is the capability to generate some control force independently on the control moment, and on the other hand, ensuring also the gravitational compensation. Otherwise, your platform cannot fly, actually. And if rotor configuration matter, in our case, propeller tilt angle matter, okay? So now we focus on this space, on the space of the control force. Better, we want to focus on the force independent from the moment. So we focus on the space FB. I remember you, that is the space of the zero moment control force. As I said, this is given by all the vectors that can express as the product between F and such U, which is limited within the space UB. And from a geometrical point of view, this space is actually a finite polytope. A polytope is a three-dimensional shape, exactly, in a shape in the 3D space. Okay, cool. We can try to explore, to investigate this space from with a geometric approach. Well, we have taken into account a specific platform. So in this case, we have fixed some of the coefficients that you see before in the model. And we can plot the shape of this space varying our angle. As you can see, if we vary alpha with respect to beta, we have actually a very different effect. So if we have alpha and beta equal to 0, this space is just one direction, okay? If we increase this angle, we have not only a direction, but a 3D polytope. So we expand this space. And the effect of alpha is really more effective with respect to beta. So the cant angle seems to have a bigger effect with respect to the dihedral. The dihedral seems to be quite negligible in this sense. And that's why we move to the part 1 of the presentation that focus on the role of the cant angle. But before, just a snapshot of the take-home message of this first part. We have that the space of the zero moment control force is represented by a polytope, we have that the effect of the dihedral angle seems to be quite negligible. So let's move back to the polytope. Can we use the volume of such polytope as a key performance index to measure the maneuverability of our platform? So as I said, let's focus on the cant angle. So we have only the alpha, so we tilt only on the direction of the arm. In this case, we can simplify the expression of the force providing zero moment. And specifically, we can introduce this matrix H, which is a 3x3 matrix, because we can characterize the meaning of the B matrix, the definition of the B matrix that corresponds to the kernel of the M matrix. And so it is quite easy to figure out the shape of this polytope, because we can express it, take into account the combination of the column of such matrix H and evaluating the varying of such coefficient U within the set U, defining the minimum and maximum spinning rate you can achieve. Okay? So it's really mathematical stuff right now. In this case, we have a finite polytope which is bounded and convex. And it is possible to measure the volume of this polytope in a closed form way. So in this case, the polytope has a specific shape whose boundary corresponds to the direction along which you have the maximum in terms of spinning rate of your propeller. While if you vary between the interval from 0 to the maximum, you have all the vector inside. So we are picking the volume of this polytope, okay? As you can see, this value vary with respect to alpha, but here we have an issue. Two different values of alpha provide us the same value in terms of volume. But the two polytopes are very different in terms of dimensional characteristics, so in terms of height, width, and depth. And specifically, if we take into account the plane indicating the gravitational compensation, we have that in one case, we have the intersection between the polytope and the plane, and in the other, no. So in this second one, we have no force that can compensate the gravity, so we have a problem. And okay, we have an issue. We have to choose another performance index. So let's try to investigate the extra overing zero moment force space. So we take into account the second aspect that I mentioned before, the gravity compensation. And we have to take into account the overing plane and pick the intersection between the polytope and such overing plane. So also in this case, we have a mathematical formulation of the vector inside this space. And specifically, what we want to investigate as a first things, using again a geometric approach, is the area that describes the intersection of such a polytope with a plane. Of course, varying the parameter defining the geometrical and aerodynamical property of our propeller, we have that it is possible to define the interval of definition of the alpha angle in sub-interval. So we have three different cases. Case A, in which you can use just a pair of propeller to compensate the gravity. Case B, in which you have to use at least two pairs of propeller to compensate the gravity. And the case C, in which you have to use all the propeller to compensate the gravity. Okay, so at least two, at least four propeller, at least 6 propellers, so all the propellers, okay? And as you can see, we have different different situations in terms of intersection between the polytope and the plane. In blue, we have the geometric shape of this intersection. As you can see, in the case A, in the case C, such intersection is a triangle. In the case B, it is an hexagon. How to determine the vertex of this shape, it is necessary to take into account the maximum and the minimum force component on the plane Fx and Fy, so the two components of the force on the x and y plane, okay? We focus on the maximum and minimum, and we can figure out the various p that define the vertex of such a shape. On the picture you see also two circles, an orange one and a green one. The orange one is the inner cycle, and specifically when we take into account this inner cycle, we are taking into account the platform robustness, because we are taking into account all the space on which you can define the two components of the force having the same magnitude. While if we take into account the outer cycle, so the green one, we are taking into account the extreme of such force components. So we are taking into account a measure of the aggressiveness of our platform. Also in this case, we can find out the mathematical expression of this index. I don't want to go into the details, just to give you the idea that it is possible to figure out all from a mathematical point of view. Again, we assess these two performance index. On one case, if we look at the value of the area, we have an asymmetric trend, and the same is also valid for the two radius, okay, so the inner and the outer radius. So again, let's try to move on and continue our investigation of such an extra overing zero moment control force. And here the things are more complicated, but again follow a geometric approach. We take into account the intersection between our original polytope and the half space defined by the plane. And again, we can have some geometric consideration, take into account the different point and reasoning in a proper geometric way, and we can figure out a mathematical expression for such an extra overing control volume. And this volume is again an asymmetric curve, but now we have several performance index. We have the volume, we have the area, we have the radii. Okay, so what we have to assess? Well, the answer is always the same. It depends. It depends on what you are interested in. If you are interested in the aggressiveness, if you are interested in the robustness, if you are interested in ensuring a big extra overing space. So this kind of investigation of maneuverability has two objectives. The first one is to provide some guidelines for designing the platform. So you want to design your platform in order to ensure a certain level of aggressiveness. Okay, you can select your angle in this way. The second goal is to assess actually the performance of existing platform. Okay, so we have this double aspects. Take a message of this part. So the volume of the polytope itself, it is not a good performance index. There exist multiple good enough performance index that depends on the alpha selection, and that depends on the application case. There exist other K performance index that could be better. Of course, the answer could be yes. We have to investigate it. It's still an ongoing work. But before the conclusion, second part, super short, just one slide about the dihedral angle. Okay, it is not so effective in terms of this polytope volume, but it is necessary for something, and the answer, of course, is yes, because it is related to the robustness of our platform, defined in terms of capability to realize static overing, so stay in a precise position with a fixed orientation, so null angular velocity and linear velocity, even if one or more propeller stop spinning. So we have the complete loss of a propeller. And what we have, that a standard coplanar Hexarotor is not robust at all. An Hexarotor on which we tilt using the cant angle is not robust at all. If we tilt using the dihedral angle, we have that our platform is fully robust to the loss of one propeller. So if you lose one of the propeller of the platform, it is still able to fly. Moreover, it is also partially to the loss of two propellers. So in some specific case, when you lose two of them, a pair of propellers, you can still be able to fly in static hovering condition, which is a kind of safe condition if you want. And so, final, the take-home message in this case is that the dihedral angles is not totally to be neglected because it is still okay to ensure the robustness. But here the question is, there exists some other configuration of the angle that can improve maneuverability. At the beginning, we did a very strong assumption saying that, okay, we tilt all the propeller inwards or outward with the same angle. Can we have different angles for the different propeller and in some way to provide some more maneuverability? Again, ongoing work. So that's all from my side. Thank you for your attention.
Thank you, Giulia. Questions from the audience?
Too much mathematical detail, I know. I'm sorry.
The direction of spinning of the rotors
Yes.
doesn't play any role in this.
We assume that they can spin just in one direction, the positive one.
Right, so they all spin in the same direction.
Exactly.
And this is typically generating the moment, I guess.
Yes, they are alternate spinning,
Okay. All right.
but they cannot invert.
Yeah, but if you change the angle, you know, if they're all vertical with alpha and beta equal 0, if I understand correctly,
Mhm.
then you can, you know, using this trick, you can zero the moment if everything is supersymmetric. But if you
Yeah.
start actuating alpha and beta, then you lose this.
But we did some assumption on the configuration of alpha and beta that still preserves some symmetry in the platform, and so in this way you can preserve the fact that you don't have the emergence of a torque moment. Yes. Well,
Other questions? Oops. Okay. So thank you again.
last speaker is our super local host, Davide Invernizzi, please.
Okay, thank you, Giulia. So it's not fair that I have to present while organizing the workshop. Okay, I'll do that. So my talk is actually about UAVs that have propellers that can be tilted. So with respect to what Giulia just presented, now the propellers can actually be tilted actively. So the main difference is that now we have a dynamic system that is added on top of the platform. So here I'm mentioning some of the main configurations that you can find in the literature. I'm pretty attached to the first one that you see here. It's a tricopter. That is actually the first paper that Marco put on my desk when I was a young PhD student. So that's why I'm keeping to it. And at that time, also, Marco was developing in the lab a first prototype of what you see on the right, which is a quadcopter tilt-rotor UAV. This is the second version that we have now working in our lab. So now we are a young PhD student with such a wonderful, platform. Okay, you're very, happy to work on it. And yeah, the path was not that simple, and I will show you the steps. So the talk wanted to talk about adaptive control, but actually what I did was to collect, all the flow from the modeling up to the more advanced control design that you can find. So now here are some simulations to show you why you need actually to add, you want to add more complexity to a platform that is already actually flying. Okay, they are not working, the animations. Can you try to click on them? So essentially what you see on the left, yeah, okay, is a standard quadrotor which has no tilting active. And so if you want to track like a circular trajectory, what it has to do is to continuously change the attitude, so it's not working. Okay, you can trust me that was a quadrotor circling around. On the bottom, you see the same, but with tiltable propellers. In that case, what you would have seen is the platform in level attitude that changes the tilting of the propellers. So one thing that you can do with a tilt rotor is somehow improve the maneuverability, as we were saying before, of the platform, in the sense that you can track different configurations. On the right, okay, let's be imaginative. We have a quadrotor on the top that receives a disturbance force in the plane, in that case X and Z, that is an unmatched force for that kind of platform. So what you would have seen is like the platform tilting a lot, a large overshoot in position before getting back to the origin. On the bottom, instead, again, you would have seen the propellers tilting in such a way that you can have a lower overshoot. Okay. Let's see. Oh, wow, magic. You can start all of them together. You know, I'm the one separating you from lunch, so of course it's not good, and having technical issues is definitely not good at all at this point. Okay, you see the tilting and then the final one, the tilt rotor. I was using the same control laws, the same gains, just to be fair. Okay, it's a different actuation mechanism that you see in place. Okay, thank you. I've got a lot of videos, so hopefully you won't have to do this often, but who knows? Okay, so let's start with some. If you can go full screen. Mathematical details behind, the modeling of these systems. So I see some of my students in the room, so they know some of this. So, okay, you have a recap here. So how do we model the configuration space for a system like this? Clearly now we have a multi-body system, right? Because we have a number of propellers attached to a central rigid body. So the first thing that we want to do actually is to control the orientation and position of a frame that is attached to a point within the airframe of the system. And what you can do clearly is to take like a position and then the orientation. And one nice way of looking at the orientation problem is to consider directly rotation matrices instead of like Euler angles. This is because then the kind of models that you will derive can be described uniquely and globally with this representation. Well, you can do even more with this specific machine in which you can control the full 6 degrees of freedom for this platform, is to unify attitude and position all together. And here, in this department, actually, they were working a lot on this kind of representation of the motion of a rigid body, Professor Boyri. In this way, you get the chance of treat in a unique way attitude and position, and that's very convenient, as we will see later. Now, this is just part of the description. We have the propellers that now can be, tilted. So the first thing that you want to describe is the tilting, and I'm using the N to denote the thrust axis. So that's the axis through which thrust is produced by the propeller, and we can change the direction of the thrust axis by playing with the tilt angle, what I called here as theta. Okay? Of course, in order to fully characterize the description, we also need an angle for the spinning of the propellers, but this is, let's say, not so important, because typically you assume this has to be like disks, so you lose the dependency in the equation from this variable. So one important thing that I want to highlight immediately is that actually by actively changing the thrust axis direction, we can change in the airframe the direction of the force that's produced. Now let's do a recap on the configuration space. So we have our multi-body system, and the manifold that we are using to describe the configuration is this one. And if you are familiar with differential geometry, they call the motion of the frame the base, and what's on top of it, the relative motion is the shape. So we've got base variables and shape variables. And this is a 6 plus 2 times n dimensional manifold. So clearly when we are using a 6 times 6 matrix to describe the frame motion, then we have a redundant parameterization. One other thing that I want to highlight that I didn't discuss, in practice, in prototypes, you don't have the angles that can be tilted as you like, so you have some constraints on the angles. Now let's see how kinematics is described. On top you see here the kinematics for the frame, so P and R, not the correspondence with the description using the 6 times 6 matrices belonging to the special rigid group with respect to the attitude kinematics. So that's really, really nice. We have here a generalized 6D cross product in place, and the velocity that we are using refers to the body frame. Right? This is called twist in the literature. For the shape, well, if you want to confuse the audience, you use attitude vectors, so two-dimensional vectors to describe a rotation. Well, let's stick to angles. That's maybe clearer. Okay, and also let me highlight that, as Julia was saying before, propellers spins in just one direction typically. So I just want to highlight that the spinning rate for the propeller is fixed. Okay. We got the description of the kinematics. Let's see now how we can describe the dynamics of the system. So that's where the applied thrusts are modifying the behavior of the system. These are Newton-Euler equations, where what I'm highlighting here is the dependency on the generalized mass matrix on the shape variable. So this is just a mathematical representation of the fact that if you tilt the arms and the propellers, then you will get a different inertia and static moment with respect to the body frame. What about the applied wrench? Well, it's a combination of different terms. We have for sure gravity. That notice depends on the attitude, because we are looking things from the body frame. We have Coriolis centrifugal terms that I'm conveniently not showing here because the expression is really complex. And finally, at least for this slide, we have aerodynamics, WA. Okay, so now you have a background in space engineering. You recognize that actually this is nothing but a spacecraft with variable speed control moment gyroscopes, and you could have saved some months of your PhD in deriving the equation from scratch, as I did, okay? But yeah, at this point, you also realize one other thing, that while in spacecraft attitude control, you really want to play with this guy to control the system, so the Coriolis centrifugal terms. Here, actually, you have some simplification in place to be considered. First of all, the shape dependency is not really important. I mean, if you have a configuration in which the tilting is done through principal axis and the arbs are like symmetric, the mass of the propeller is not that large, well, you can really remove it when you are trying to come up with a model that is control-oriented. At the same time, this depends on the inertia. You use those in order to control a spacecraft. Here, they are just disturbances, so you take care of them. And then there is the aerodynamics. That is a question mark, in the sense that modeling it is really not my job, and I mean, it's complicated. You have to think about that. You have propellers that are tilting and interacting with the air. How can we come up with a reasonable model to characterize the dependency on the variables here? Indeed, what you can do at best, and this is what we have seen also in the literature, is to take for small space like a linear damping dependency on the twist. Okay, I talked about the three main ingredients for the applied wrench. Now let's move to the actual variable that allows us to control the motion of these systems. That is the control wrench, which is made of two terms, the force and the control torque. Julia already showed this basically with a different notation, but yeah, I created the PP variable here, okay? Just at the end of a difficult process in finding the best way of representing this equation. This is nothing but, the sum of forces along the thrust axis direction. And then for the torque, what you have to do is to transport the force with respect to the base, center, and then to add the pure torque related to the spinning of the propellers. And what it is nice about this model is that you can factorize it in this form here, where now we have separated the dependency from the tilt angles and the thrusts of the propellers. But this is a nonlinear map that we have, differently from what Julia showed before, because now θ1 up to θn are actually variables that you can play with. Now, there is another thing that I didn't talk about, that is, okay, we have propellers, they have motors, and we have servo actuators in order to change the tilting. What about their dynamics? So we are totally neglecting that. Well, what you can do, at least based on my experience, is that a first order model is sufficiently accurate in the flight condition that we are considering. And yeah, in this way, we have the full simulation model that is like a cascade of this form, in which we have access as control variable to the thrusts that you can produce, that you can command to the motors, and the tilt angles. So these are our actual physical inputs. These physical inputs are transformed through the wrench map to the applied control signal that goes into the flight dynamics. Now let me do some comments on what we just derived. We have a system whose kinematics evolves in a nonlinear manifold, and as we have seen this morning, we have some topological abstractions that we might have to deal with when doing control. On the other hand, the dynamics, the second equation that you see there, is evolving in a linear manifold, but it's nonlinear as the dynamics, and it's uncertain. So that's where you have parametric uncertainty and disturbance is appearing. Finally, the system can be underactuating depending on the actuation configuration, the limits that you might have on the tilting of the actuators. A nice control problem. Now, how do we approach a control design for motion control for a system like this, in which, let's say that you have some guidance function providing you your eye-level goals? Well, we got overactuation somehow. We have 4 N servo motors and propellers. We have a system that is nonlinear. Well, one could think about, going through a holistic approach like MPC, which you put like the constraints that you have, your nonlinear dynamics, and try to, control the system as a whole. That's actually an approach I'm not familiar with, and you have also to take into account the fact that, you have your prototype that has been built with effort, and when testing something completely new out of the box, that's dangerous. So you also know at the same time that there are some control structures that works well for this kind of systems. So it's maybe better, to start from something that you know and then improve on it. And this is the 2-level design that I'm proposing here. that is a hierarchical design in which we have a motion controller that tries to compute, in a sense, the force and torque needed to achieve the mission goals, and then the allocation function that tries to optimize, to split across the different actuators, the control action commanded by the motion control. I've quotation marks there because I'm taking this quote from Andrea Serrani. This approach is nothing but control first and optimize later philosophy. And what it gives you is a lot of modularity. So in the end, what you can do is to have several substructures that are interacting, and then you can work on individual substructure in order to improve them or to change their behavior. But you don't have to throw everything away. So that gives modularity, which is something very, very valuable. And this is also the scheme that you find in aircraft control systems. That's the typical setup. This is just to tell you that this is a basic scheme. You can do much more than this. And for instance, if you have signals from the actuators or models, you can, refine the allocation block to be, to include some fault tolerance and stuff like that. For instance, this is just one example of the flexibility that these schemes gives. Now let me just give a few words about the allocation problem. So that's the problem of converting, the motion controller output into the actual commands that you want to give your actuator to. The physical inputs, as I said, are the thrusts and the tilt angles of the propellers. The actual inputs, so the outputs of the actuator dynamics, I'm calling that UA. The typical assumption that you do in deriving a control allocation block is to assume that actuators are fast enough. So you have a quasi-static approximation of your control action produced by the actuator, so that basically the range map now becomes just a function of the commands variable. So you remove the actuator dynamics from the picture, at least at this stage. Note that the imperfect allocation that comes from this assumption can be somehow mitigated at the motion control level side. So taking into account this in the higher variables. Now let me show you an example of an allocation for a quadrotor, a quadcopter tilt rotor. Sorry, this is the range map that you get in that case, in which you have a factorization where the first matrix depends just on geometry. You see L is the length and gamma are the orientation angles, and then there are some aerodynamic coefficients, but this is something like parametric fixed. And if you, in this case, we have that the rank of this matrix is 6. It's a 6 times 8 matrix, and the rank is 6. But then we have a nonlinear map here. So what we need to study actually is the Jacobian. And you see that the Jacobian depends on the product of the thrusts. So we have a full roll rank Jacobian, meaning that we can locally invert the function if the thrust is non-zero commanded to the propellers. And actually, there are cases in which you can get to this condition. Think about having the tilt rotor with one arm that is aligned with the gravity. In that case, you are trying to make hovering, then you are not required to produce any force in that direction. So the propellers that are on top and the bottom, they will be commanded to have zero thrust if you try to minimize the total thrust. And then as soon as you have perturbation, you will see the propellers that are trying to do something like this. So that's really not well defined map in there. So let me show you a basic 101 allocation strategy. Well, pseudo-inverse does the job here. So we have our W matrix that can be pseudo-inverted. We compute a FU that collects the component of the thrust you see along the Z and X axis. And then once you retrieved this from the pseudo-inverse, then you can compute using the ATAN2 function, actually the angle and the thrust that you have to command, given the applied range that you want to, the control range that you want to apply to the platform. So clearly here we have two solutions. You might want to take just the feasible one. We have unidirectional spinning propellers, so the positive direction. And note that we have an indeterminate system when t is actually equal to 0. And this is called kinematic singularity in the robotic community. We are not assuming to be in that condition. So let's say that our flight envelope does not go in that region. That is quite reasonable for the machine that we have. And so we can like safely say that the virtual input that we can assign to the system, it actually spans R6, provided some bounds, you know. We have a squared system if the output is taken as the configuration of the rigid body the rigid body corresponding to the UAV. This means that generic post tasks like solving trajectory tracking can be done. So let's say that we are given a differentiable curve in SR6, then we can invert the system and compute the open loop input that will provide that motion. Okay. So we can go in, thanks to full actuation, we can achieve this. Now, let's see how we can come up with a control law that is robust to not just modeling errors, but also to initial conditions. And in order to derive the motion controller, what we want to do is actually to exploit one more time hierarchy in the model. And we have here a cascade structure if you look at it, because actually the physical input now, the virtual input UV modifies the behavior of the twist, and the twist can be used to control the actual pose of the system. And again, let me highlight that this approach is like, okay, good for us because we have kinematics that is evolving in nonlinear manifolds, so that's a messy problem from a control point of view, but it is free of uncertainty. And the dynamics that is evolving in a linear manifold, but it's affected by uncertainty and perturbation. So let's take the perspective of an inner-outer loop control design. And this is the scheme that we are going to show, which we have the dynamics in the innermost loop controlled by a dynamic controller that tries to, counteract the effect of uncertainty and disturbances, and then something that takes care of the messy kinematics that we have. Let me start discussing first the outer loop. So this is where we have our high-level goals. We have the virtual input, nu C, the twist, that we introduce in a backstepping-like design to the equation, so that we have a mismatch between the actual twist and the commanded twist. And then the problem that we want to solve is when we have the error of this mismatch assumed to be 0, let's try to find the twist that will ensure tracking. Right? Can we achieve a global, so I didn't place an initial condition here, can we achieve a global result? Well, this depends on the kind of flexibility that you give to your design, in the sense that if you stick to a continuous time invariant controller, that no matter what, you cannot find a global solution. And this is precisely because of topological obstructions that were discussed before. Now, we have a tracking problem, so let's define tracking errors. With the configuration variable that I'm using, they are written in matrix form, so it's the final expression for the tracking error dynamics is the one that you see here on the right. And let me highlight that this specific selection is invariant with respect to changes in the inertial frame. So if you have like measurements that are only relative, then this is good for your design. Let's now try to provide a structure for a control law to achieve our goal there. Well, we have a kinematic system, so let's use the simplest approach use a static feedback with feed forward. We need the feed forward to take care of, of the desired velocity that we have here. In that way, the aerokinematics will evolve according to this perturbed equation, where in blue you see highlighted the stabilizer, and we have freedom in selecting the stabilizer, provided that it will give us some, stabilizing properties and robustness properties with respect to the perturbation. The simplest approach, again, that I'm reporting is based on a negative gradient feedback. And it's based on using, a Lyapunov design using this function. Sorry, I'm late. I jumped the details. This is widely used in the field. The gradient has this shape. The issue is that this is a continuous stabilizer. So if you evaluate it at 0, then you discover that you just don't have one equilibrium point created in your system. You have 3 additional equilibria corresponding to 180 degrees of freedom rotations. So that's why you really cannot achieve global results with this design. What you can do is to achieve an almost global stability result, which means that the set of initial conditions that will bring you to the unwanted, undesired equilibrium points are like of 0 measure in the state space. Then we can do something more. Since we have a Lyapunov design, we can show that we have uniform ultimate boundedness of solutions for this system. And then thank you, David Angeli and Prali, for this result on almost input to state stability. So we have robustness as well to zero gas, so zero asymptotic, global asymptotic, almost global asymptotic stability with 0 inputs. Now, for the inner loop, the design is simpler at this point because we have a linear manifold now. UV can be selected according to a static, design, which is parameterized in terms of this gamma nu with the green. So I'm not as good as Luca with colors. Sorry for this. This is a static feedback stabilizer. But let's say that you have perturbation. So maybe here the generality that you have to include as to consider also a dynamic state, so a controller state. What about the closed loop error analysis? With Luca and Marco, we had some fun in the last year in studying the cascade resulting from this design, in which we have the inner loop aerodynamics that is perturbing the kinematics in this form. If you are good enough in providing good selections for the stabilizers, then you can achieve a globally asymptotically stable behavior for the upper subsystem, and then you have almost ISS thanks to the previous results for the kinematics. And then again, there's a theorem here that you have gas and almost ISS, and then this provides almost global asymptotic stability of the cascades. Now, let me make a comment on the almost. So what I said is, okay, basically the chance of converging to the undesired equilibrium is null. But is it good when I have to test it on a real machine, or will I get in troubles? Well, let me say a few things. First of all, we have, using this description of the kinematics, a globally well-defined continuous control. That's desirable. In my experience, it's really hard to get stuck or converging to undesired equilibrium because you have perturbations that are never keeping you exactly in the undesired configuration. This is just one part of the story, because we have also a Lyapunov that is helping us in providing maybe an estimate of the region of attraction for our design. So we have like exponential stability guaranteed within a bounded domain. So that's nice. But there is a but. When we try to push the kind of motion that you want to achieve with your platform, then you might encounter performance deterioration. We have non-uniform convergence resulting from these controllers. That's why, together with Luca and Marco, we try to, provide an high-performance design using hybrid theory. In that case, well, we recover global results, uniformity, that's good. But we have a significantly more complex analysis that must be done, because now we don't have really a cascade or a pseudo-cascade as in the continuous case. We have this hybrid feedback in which the flow perturbation is going in one direction and the jump perturbation in the other direction. So yeah, the difference with respect to the before is that now we have to rely on Lyapunov tools in order to, achieve the final result. Instead, before, everything here was relying on structural properties of the control system. Okay, so I'm late, I guess. Okay, I got, no, I didn't talk about adaptive control. Oh, oops. Okay, baseline control design, let's pick a selection for the structures that I've shown before. You can prove that actually the inner loop behaves like a proportional controller. So we have, with our simple design, we are able to replicate something that we know will fly. Okay, and this is ensuring when you are testing your prototype. These are the results that we obtain just with the manual tuning. So with a very clever, pilot testing the design the first time, we had still a platform that can fly. And these are just the attitude variables. So you see roll, pitch, and yaw. Maybe the performance are not that nice. So let's see. Okay, we don't have time for the video. It won't go, I guess. Okay, let's keep it. Well, now we can play with this design, because maybe, given the structure, we can apply some well-known tools to improve performance, like tune the gains using mixed sensitivity. So now that we, we have some experience on the machine, and we have a model that is more reliable. We collected data from the previous experiment, and then we obtained something that is better in terms of performance. You see, we remove the undershoot basically. But still, this platform has some couplings in the yaw axis that you see here that are not very good. Let me try to explain why this happens. This is because when you place the battery, maybe you are not very accurate in positioning it behind the drone. And then you have a moment appearing. And this is, with this machine that you can keep hovering while tilting, you see a disturbance on the yaw axis due to this mismatch that we have in the center of mass with respect to the geometric center. And note that with integral control, actually you cannot solve definitely the problem, because the third component of this torque depends on the attitude. So when you are maneuvering, you just see the other two components, and so the integral states will react just to that component. Okay, go very fast on it. Given the model for the attitude dynamics, we can get out a model, a certain model in the form suitable for adaptive control by creating a standard linear in parameter form for the part related to the static moment. Standard setup for MRAC design. We have a plant, we have a controller. We create a reference model based on the plant and the controller design that we have, that were designed on nominal conditions, disregarding the effects of the static moment uncertainty. This is called augmentation problem. It was addressed by Labretsky several years ago in this form, which you try to find a control input that acts on top of the baseline. This is nice. This is a plugin feature that you want when testing something, really new. And these are what you ask your designer, the basic stuff that you can get from standard MRAC design. So boundedness of forward solutions and the reference model error that converges to 0. What we tried to address recently is the plant augmentation problem, in which you don't want to embed within the adaptive design the states of the controller, so that you don't need that information that maybe you don't have access to. And again, you want to achieve the same goals. Is this solvable? Well, we have an incoming paper at CDC as well. That's about this design, so I don't have time to go really through it, but it's a predictor-based adaptive design. You see, what I want to highlight is the structure. You have the baseline controller at the plant. The only, let's say, connection between the adaptive loads and the baseline controller are the output of the baseline controller. This is like, similar to the compensator design in anti-wind-up, in which you want really to add the adaptive component just when you have a mismatch with the intended behavior. So you need not to know the baseline controller structure and states. You have a reduced dimension with respect to a full design. You have a plug-in feature that's nice. So when we are testing it, we can place here again, going to 0 if something bad is happening, and we have still the baseline active. When in saturation, we have the predictor that is informed, so it won't wind up. So we have this anti-wind-up property in place. Okay, this is where I show you why it works, but it would take some time. So I guess you can find it in the paper, which is on the letter, so it's there. But yeah, just this, we have a cascade. Okay, we have still a cascade that we can rely on for the stability analysis. Here you have standard system that you would get from an MRAC design with boundedness of the prediction errors, the convergence to 0 of the prediction error for the state, and then the perturbation on this modified reference model error. And yeah, that's the theorem, okay, that you can read on the paper. Results, let me thank the PhD student that patiently worked on the machine. You see, here we have several steps of pitch angle. The first instance is the baseline design. This is what you get from the heading. You see, we have some overshoot in the heading that is not intended to be there. Right after the baseline, we activated in flight the adaptive part. You see, we obtain definitely better performance on the main axis, the pitch axis that we were commanding. And you see then a decrease in time of the coupling between the axes. This is the learning process of the adaptive controller that in the end basically removed asymptotically the center of mass effect. I've got a video this you have to show because it's the end. Then of course I will take questions over lunch. Okay.
Is there any super quick question for Davide?
Okay.
Your Lyapunov function on slide 19, as a matter of fact.
Can you go?
You lose the video, sorry.
I put numbers at the end. I know that I didn't have to do that, so Astolfi wouldn't ask me a question. 19, ok. Cioè, fai prima tu. Yeah. So the trace tab, how do you know it's possible? I just don't understand. Yeah, of course. You need some constraints on the gain scale. So thanks for spotting it. But yeah, so the design would require to have actually like the trace of k, the identity minus k greater than 0. This would give locally a function that is quadratic and positive definite. There are constraints. Yeah, definitely. So it's not just a symmetric positive definite function. Yeah, actually this comes from like the Frobenius product between the norm of matrices, so high minus, this is not a hierarchy. You take that transpose times the same non-transpose, and then you can show that you can get to this by exploiting the fact that RE, transpose times RE is the identity. You get down to like something that looks linear, but that's quadratic actually. So it comes from a scalar product. Okay. Okay. I told you. Thank
you.
Sorry for
the speaker again.
Thank you. Okay. thank everybody for. I don't know if Alessandro, you want to say anything to conclude the day, or to just conclusive remarks.
Witty remark at the
Can
end.
you come here? Sorry.
Yeah, okay. Well, thanks a lot to everyone for the nice presentation and for being here. So I sort of recall we started writing this project during COVID. So it was a full Teams, in Teams, effort. So, but we were very pleased with the outcome, and clearly I think we've done some very good work. So thanks to everyone for this. Thanks to you for attending this meeting, and thanks to all those online. And thanks to the organizer.
Thank you also. Thank you, Laura and Donato, for assisting us today with the technical stuff. Thank you very much.